Okay, last time we have seen how we can calculate the deformations of a member under axial loads and under bending moments. Now let's see how we can use these equations to calculate the deformed shape of a structure. Now I will be working on a structure as an example that is composed of two members. So I have a column, that's a determinate structure, a beam, and I have a uniformly distributed load on that beam. 2 kilonewton meters. The length of the beam is 3 meters, and the length of the column is also 3 meters. Okay. Now here we'll assume axial rigidity. Of course, we will give that to you. And EI is the same and constant for all members. Okay. Now let's do the discretization. Let's divide this structure into nodes and members. So a node here, another node here, and another node here. And the way I'm looking at this structure is as follows. And let's say that this is my first member, this is the second member. Now I'm using arrows. These arrows will help me to figure out the local coordinate axis of this member. So this is the local x prime. This is the local y prime. I will use these local axes to write my differential equations. This is local x prime for the first member and local y prime for the second member. So these are the local axes and these are the nodes. Now let's determine the degrees of freedoms. Now here we will use these degrees of freedoms while we are interested in the deformed shape of this member. And axially rigid, that's no degrees of freedom here, fixed support. Now I'm at this node. Can it translate in the horizontal direction? The answer is yes. That's my first degrees of freedom. Can it translate in the vertical direction? The answer is no, because this column is axially rigid. And can it rotate? Yes. That's the second degrees of freedom. Let's go to this node now. Can it translate in the horizontal direction? The answer is yes. That's D1. Why D1? Because these two ends of this member should translate the same amount so that I don't see any elongation or shortening on this member. So I have D1 here. Can it move in the upward direction or the vertical downward direction? The answer is yes. That's D3. Can it rotate? Yes. That's D4. So in this structure, I got 3 nodes, 2 members, and 4 degrees of freedom. Okay, now let's draw the free body diagram now. Member node, and the other member node. So the support reactions, the vertical support reaction is 2 times 3, 6 kilonewtons. And in order to balance the moment due to the uniformly distributed load, I should have a moment in this direction. and its magnitude is 9 kilonewton meters. Now I'm writing the equilibrium for the node. That's 6 and 9 here. Transfer it to the node. I'll have the same axial force, 9 kilonewtons, and moment that's equal to, again, 9 kilonewton meter. So I'm at the top of the member, it's 6 again. I don't have any shear force on this member, so I should have the same moment, but in the opposite direction. Now this member is in equilibrium. Now let's take a look at this member. In order to go to that member, I should be transferring this force here, moment, same moment, force in the downward direction. At this end, again, I have 6 kilonewton in the upward direction and a moment in the downward in the counterclockwise direction, and no force at this end. Okay, and I should also forget to show that we have a uniformly distributed load here. All right, so I draw the free body diagram. Now this member is axially rigid, right? We are ignoring the shear deformation, so I'm only interested in the bending deformation. And according to our previous discussion, the bending deformation is caused by the moment. So in order to determine that bending deformation, I have to draw the moment diagram. So let's draw the moment diagram now. And I will be using this sign convention. Let me draw it in here. Plus, that's my sign convention for the moment. Let's draw the members. So I define my first member going from bottom to top. So let's show it. It's going from bottom to top. Second, from left to right. So it's this way. Now you have to be careful. These directions should match these directions, because that's the way we will write our differential equations. All right, now let's show the moment diagram. I'm just rotating this sign convention by 90 degrees. So if I do that, my positive directions will be as follows. And these two moments are in the opposite direction with the positive moment. So I have a negative moment and a constant moment. That's minus. And this is 9 kilonewton meters. Okay. Now, here in this member, I have minus 9 moment at the beginning and 0 moment at the end. So minus 9 here, 0 here. What about the variation? Variation is, I got 6 kilonewton shear force here and 0 here, and this is a positive moment, so the moment should increase. How? I have the highest slope here and 0 slope in here, so the shape should look like this. That's the moment diagram. Okay. Now let's take a look at our governing equation for the bending deformation. We are saying that the second derivative, of y with respect to x is equal to moment divided by EI. So in order to solve this governing differential equation for these members, I need the equation of the moment. So now in order to derive the equation, I need a coordinate axis. So the first member goes from bottom to top. So that's actually, my origin is here. That's x prime, right? And for the second member, you go from left to right. this point is our origin, and it's in this way. So according to that by using this coordinate axis and this origin, I will write my equation for the moment, and for this one, m of x prime is equal to a constant moment and magnitude is 9 kilonewton meters. And in this one, m of x prime is equal to, so when x is equal to 0, the moment should be -9, so I have -9. The shear force here, right, should decrease the moment as we move along the x prime axis, so I should have plus 6x. And the uniformly distributed load, if I take a section cut here, will create a moment in the same direction with this one, and the magnitude of that moment will be 2 times x times the moment arm will be x over 2, and I got minus x squared. Now, if you cannot directly write this equation, you can always do this. Let me use a different color. You can always take a section cut and do that. Right? I have a uniform distributed load. That's 2 kilonewton per meters. That's the moment m. I have a shear force here, 6 kilonewtons, and I have a moment here, 9 kilonewton meters, and this is the x prime axis, and take moment with respect to that point, and at the end of the day you will get this equation. Okay, now I got two members and I know the bending moment at each member. Okay, and I need to solve this differential equation, right? Because this differential equation will give me how much rotation that I will have and how much transverse displacement. It's all in there. I know what the moment is, and by solving that differential equation I can determine dy over dx and y equations for y. But in order to solve this differential equation, that's the second order differential equation, so I need two boundary conditions. So if you take a look at this member now, our first member, right, at the start node, I know that the vertical translation y should be equal to 0 and rotation dy over dx is equal to 0. So if I know, since I know these two boundary conditions, I can actually solve this differential equation for the first member. Once I determine the equations for the transverse displacement and rotation for the first member, I can determine the values of d1 and d2. Okay, then I can jump to the second member. Again, use this differential equation. This time I know the values of d2 and the vertical translation is equal to 0 at x is equal to 0. So again I know two boundary conditions and I can solve this equation, and once I solve that equation I can determine what d3 and d4 is. That will be my starting point. So let's solve that differential equation for the first member. Okay, member 1. So this is node, this is our member. I just draw that member in the horizontal axis like that. Okay, so what I did here is I draw this member 1 as follows, right? That will be the x prime, that will be the y prime, and I have a node here, right? And according to, if I rotate that, d1 will be in the downward direction and d2 will be in this direction. So let's show it in here. That will be the d1, that will be d2. So these are the degrees of freedom in the structure. That's my x prime axis, and that will be the y prime axis. Boundary conditions, so at x prime is equal to 0, y prime is equal to 0. What else? dy prime dx prime is equal to 0. So these are the boundary conditions. And I got two unknowns, which are d1 and d2. So let's write the differential equation. So d square y dx square is equal to, moment is minus 9 divided by EI. Okay, that's the governing differential equation for the first member. Now integrate that member once. So I obtain dy over dx is equal to minus 9x divided by EI plus C1. So in order to determine the value of C1, I can use the following boundary condition. At x is equal to 0, dy over dx is equal to 0. So from that, at x is equal to 0, I forgot to put primes here, we should have all primes. Dy prime dx prime is equal to 0. This tells me that C1 should be equal to 0. Okay, now integrated one more time, I obtain the equation for the transverse displacement is equal to minus 9x squared divided by 2EI plus C2. Then I can use the first boundary condition to determine the value of C2. Let's do that. So at x prime is equal to 0, y prime is equal to 0. So this tells me that C2 is equal to 0. So for the first member, the equation for rotation is equal to minus 9x divided by EI. So there's a linear variation in rotation. And the equation for transverse displacement is minus 9x squared divided by 2 EI. Okay? Now, I need the values of d1 and d2. So I have to calculate this rotation and the translation at the end of the member. Remember that this distance is 3 meters. So at x is equal to 3, dy over dx is equal to minus 27 over EI, and y is equal to minus 40.5 divided by EI. Let me draw the deformed shape on this member. So we are saying that this point cannot move. The end node should move in the minus y direction. And we are here. And this distance is 40.5 divided by EI. And the slope at that point, that's the slope. Sorry, that's the slope. And the magnitude of that rotation, it's minus, meaning that it's in the minus z direction, or in other words, it's in the clockwise direction. I have a clockwise rotation and the magnitude is 27 over EI. What about the variation? Variation of the transverse displacement is quadratic. So I have zero slope here and then it moves this way. So that's the deformed shape of the first member. Now let's determine the values of d1 and d2. So d1 is equal to, now remember that that's the direction that we choose for the d1. This is our positive direction for d1. And according to our calculations, it moved by 40.5 EI in the same direction. So since the translation and the direction of the d1 is the same, so the magnitude of d1 should be 40.5 divided by EI. And our positive direction in D2 is plus Z. Now we see a rotation in the minus Z direction. So D2 should be minus 27 over EI. Now we determine the values of the first 2 degrees of freedom. If we go back to our figure here, the discrete version of the structure, now I know what D1 is and I know what D2 is. Now take a look at the second member. At the start node, now I know the amount of rotation and the transverse displacement is equal to 0. It's known. And again, in order to solve this differential equation, all I need is the values of 2 boundary conditions. So let's solve the second member now. So let's draw it again. This is the second member. Its local axes are as follows. That's the x prime. That's the y prime. So let's draw the degrees of freedoms. Here I have D1. Here I have D2. D1. D3. And D4. Now let's write the boundary conditions. So at x is equal to 0, no vertical translation, we have an axially rigid column, and the rotation, we already calculated it, it's equal to D2, and the magnitude of the rotation is 27 divided by EI. Now I can write the differential equation. D square y divided by dx square is equal to 1 over EI times the equation for the moment. And the equation for the moment is minus 9 plus 6x minus x squared. That's the governing differential equation for bending deformation. So we will do the same thing. I integrate it once. dy over dx is equal to 1 over EI minus 9x plus 3x squared minus x cubed over 3 plus C1. Okay, that's the equation for rotation. Now at x is equal to 0, we know that the rotation, let me put the primes here, I always forget, sorry for that. Dx square, is the rotation is equal to minus 27 over EI. This tells me that you put it into that equation by putting x prime equal to 0. This will give you C1 as equal to minus 27 over EI. Okay. Now integrate the above equation one more time. Y is equal to 1 over EI again. So minus 9 over 2 x squared. I'll not put primes, you know that they're all primes, so let's not waste time with that. Then 6x cubed, it's 3x cubed over 3 minus x to the power 4 divided by 12 minus 27x plus C1, C2. So at x is equal to 0, y is equal to 0, this tells me that C2 is equal to 0. So our equation for the rotation dy over dx is as follows. 1 over EI, we have a cubic parabola, minus 9x plus 3x squared minus x cubed over 3 minus 27. And y is equal to, that will be a fourth order polynomial, and minus 9x squared divided by 2 plus x cubed minus x to the power 4 divided by 12 minus 27x. So that's the equation, variation of rotation with respect to x prime, and that's the variation of translation again with respect to x prime. Now let's draw, or let's determine what dy over dx at x is equal to 3. So at x is equal to 3, you put x as 3 into that equation, we obtain dy over dx as minus 36 over EI, and y as equal to minus 101.25 divided by EI. So let's plot that one more time. So we are saying that, so the translation here, I will not show the translation in the x prime direction. The vertical translation at the beginning is equal to 0, and it moved in the downward direction, and the magnitude is 101.25 divided by EI. Now at the beginning, we have a rotation, a clockwise rotation. Let's show it this way. That's a clockwise rotation. Magnitude is 27 over EI. At the end, that rotation increases, and the magnitude is 36 over EI. Again, a clockwise rotation. And we have a quadratic, sorry, not quadratic, fourth order variation in the transverse, but I'll just sketch it this way. That's what we expect to see. Now I'm looking at what's going on at that end. Now we define D3 in the upward direction, but this point moved in the downward direction. So the magnitude of D3 is equal to minus 101.25 divided by EI. And the magnitude of D4 is equal to minus 36 divided by EI. And D1 is what we already calculated before, and that's equal to 40.5 divided by EI. So as you see, once we know the equation of the moment and two boundary conditions at a member, we can calculate everything. We can calculate the equation of the rotation, and I can calculate the equation of the transverse displacement. And by using these equations, I can determine the values of all unknown degrees of freedoms. Now let's, as a final step, draw the deformed shape. So originally the structure is like that. That's the undeformed shape, right? So here I know that there is no translation, no deformation. At the top, this point move here. The magnitude of that translation is 40.5 divided by EI. This point move the same amount. This translation is 40.5 divided by EI, okay? Now I should have some rotation here, right? We said that we will have a clockwise rotation. The magnitude of that rotation is 27 over EI. And this is a rigid joint. Rigid joint means that I have the same translation on the beam also. So this translation is also equal to 27 over EI. This end move in the downward direction, and the magnitude of that translation is 101.25 over EI, and we see again a clockwise rotation by a larger rotation, just I exaggerated it, and this is 36 over EI. Here everything is 0, so we should see a deformed shape, and in this column something like that. And here that's the deformed shape of that beam. We are just sketching what's going on in the middle, but if you want, you can use the software and plot the exact deformation of these members, since you have all the equations. So that's the way we will calculate. We can calculate the deformed shape of a structure. We know all the governing equation. That's the governing equation for bending deformation. Once you divide the structure into members and nodes, for each member, remember that they should be continuous, that's the requirement. We can actually write the following equation. And for me, in order to calculate that deformations, I need to know the equation for the moment and two boundary conditions, since this is a second order differential equation. And how do these different members communicate? If we are talking about forces by using the nodal equilibrium and the section cuts here, that's through nodes, these forces communicate between these two members. What about the deformations? The deformations are communicated by the degrees of freedoms among members. And we will do more example problems, and you will better understand what we are doing here.